In this video, I'm going to discuss about biomolecules in general and specifically about carbohydrates. And in the later stages, I'll be coming back to amino acids, proteins, etc. We know that carbohydrates are the primary source of carbohydrates come from plants. There are a large group of carbohydrates that occur naturally, and some carbohydrates can also be prepared artificially. The main carbohydrates that we normally know are glucose, sucrose, fructose, etc. So, as per our basic knowledge, we know that the general formula of carbohydrates fall in the common category of CX, H2Y and OY. But there are many exceptions to this. That means initially it made us think about the fact that maybe the carbohydrates are some kind of hydrates of carbon, because it is falling in the formula of this. So it led us to think that maybe the carbohydrates are a type of hydrates of carbon, but the presence of sugars like rhamnose, which has a formula of C6H12O5, this is known as rhamnose. This too is a carbohydrate, but this does not match the formula of the formula that led us to think that it is a type of hydrate. So we delved into the depths of carbohydrates and found out that it has nothing to do with the hydrate formula, and it is a completely new branch of organic chemistry. Okay, so first we are going to classify the carbohydrates. Mainly in our textbooks it is classified as this way: monosaccharides, disaccharides along with oligosaccharides, and last polysaccharides. Now, what are monosaccharides? These are carbohydrates that cannot be hydrolyzed to give smaller units of saccharides, that means polyhydroxyaldehyde or ketone. We'll come to that again. So monosaccharides are carbohydrate molecules that cannot be hydrolyzed to give further smaller units of polyhydroxyaldehyde and ketone. So we can write that monosaccharides, if made to undergo hydrolysis, no reaction will take place because it will not break down. But in the case of oligosaccharides and polysaccharides, we will see that further simpler units of sugar molecules are formed. Now, why did we call it polyhydroxyaldehyde and ketone? Because later we'll find out that monosaccharides, or in other saccharides too, have the type of formula like this. Now I am writing a very general formula, it is not of a specific molecule. We'll discuss specific molecules later. Now as they have multiple hydroxy groups, so we are calling it polyhydroxy, and the terminal group is aldehyde. So this is polyhydroxyaldehyde, but keto compounds are also there, like fructose. I'm writing a general example. So in this case there are polyhydroxy group, means multiple hydroxy group, but a ketone group also. This leads to polyhydroxy ketone. So this definition brings in both of them inside the monosaccharide category. The monosaccharides also can be classified into various forms. Remember that we are still discussing the monosaccharides only. It is a classification of saccharides in which the saccharide can be classified into monosaccharide, oligosaccharide and polysaccharide. The monosaccharide branch can also be further classified down to these groups. Depending on the number of carbon atoms that the saccharide contains, we call it triose, tetrose, pentose, hexose or heptose. Like if a monosaccharide that contains 1, 2, 3, 4, 5, 6 carbons, we'll call it hexose. So there are triose that contains 3 carbons, tetrose 4 carbons, pentose 5 carbons, hexose 6 carbons and heptose 7 carbons. Now we know that saccharides can be two types, mainly aldehyde and the ketone part. So if the saccharide contains 3 carbon atoms and it is an aldehyde type saccharide, then we'll call it aldose, but as it is a 3 carbon carbohydrate, so we'd call it aldotriose. But if it is a 3 carbon ketone type saccharide, then we will call it ketotriose, right? So depending on the nature of the functional group present in the saccharide and the number of carbon atoms present, will define it. If it has 5 carbons, let us say 5 carbons, and a ketone group containing saccharide, then we will call it keto pentose. Yes. Now let's discuss oligosaccharides. We'll come back to monosaccharides again, as we'll have to classify them in order of number of carbon atoms and name them individually, because each of them have an individual common name. Oligosaccharides. Oligosaccharides are again carbohydrate molecules that give 2 to 10 monosaccharide units on hydrolysis. It's easier to understand this way, that oligosaccharides are polymers of monosaccharide. How many monosaccharides are present? It can be 2, it can be 10. So depending on that, on hydrolysis it will yield 2 to 10 monosaccharides. Let us suppose monosaccharides, the oligosaccharide that we are concerning now, let us say it has 3 monosaccharide units and it is a polymer of monosaccharide, so it contains 3 monosaccharide units consecutively. Upon hydrolysis we know that the monosaccharide units break down to their individual form, so 3 monosaccharide unit units will be formed. As this number lies between 2 to 10, we can call that specific oligosaccharide. This one. Let us give an example. Like we know that sucrose on hydrolysis gives one monosaccharide and another monosaccharide. So the two monosaccharides are quite well known to us. One is glucose, another is fructose. Maltose is another oligosaccharide. How many monosaccharides are present in each of these oligosaccharides? 2, because on hydrolysis we are getting 2 monosaccharides. Maltose on hydrolysis will give 2 molecules of glucose. I will not write 2 glucose because these 2 glucose molecules, though they are same chemically, there are some differences which we'll read about later. So sucrose on hydrolysis will yield 1 molecule of glucose and another molecule of fructose. Maltose on the other hand will yield actually 2 molecules of glucose, but they are structurally a little different. Next comes polysaccharides. Polysaccharides is quite understandable from the name itself. If the number of monosaccharides that are formed on hydrolysis of the polysaccharide is more than 10, that is, if there is a polysaccharide, this on hydrolysis yields n number of monosaccharide. If n is greater than 10, then this is known as polysaccharide. If the n is less than 10, then we'll call it, means less than 10 and obviously greater than 2, then we'll call it oligosaccharide. And if the monosaccharide does not undergo hydrolysis, then we call it monosaccharide itself. Okay. Examples of polysaccharides are cellulose. Like for a long time we have written this CN H2NON as the molecular formula of cellulose. Cellulose, starch, glycogen, etc. Now we'll come to the chemical part of carbohydrates. Reducing means the classification based on the chemical properties. Based on chemical properties, carbohydrates can be, or sugars can be classified into mainly 2 forms: reducing sugars and non-reducing sugars. These are the main 2 forms of sugars that are based on chemical properties classification. What do reducing sugars do? They reduce tolerance and Felling's reagent. Now what is Tollens reagent, what is Felling's reagent, we'll later understand, but mainly we need to understand right now that Tollens reagent is a salt of silver and Felling's reagent is a salt of copper, which is reduced by our sugars to form their respective precipitates, and itself gets oxidized. The sugar gets oxidized and it reduces the reagent. So, and in the case of non-reducing sugars, they won't be able to reduce Tollens or Felling's reagent. So this is the main thing about chemical classification. We mainly classify them into reducing or non-reducing sugars. Some can reduce Tollens and Felling's reagent, those are called reducing sugars, and which cannot, they are called non-reducing sugars. I can give you examples here, but later we'll discuss about how they reduce tolerance and Felling's reagent. Another thing to remember that all monosaccharides aldose or ketose, all of them can reduce tolerance and Felling's reagent. Now this is quite tricky because later in class 12 we'll read that Tollens and Felling's solution can only reduce aldehydes and not ketones, but in this case even the ketone group gets reduced by Tollens and Felling's solution. The reason behind this is quite advanced and out of our syllabus, so maybe we can discuss it later somewhere in a special lecture, but for now we'll just keep it in our mind that any sort of monosaccharide, be it aldose or ketose, be it 1 carbon or 6 carbon or 7 carbon, it will be reduced by Tollens and Felling's reagent. Oligosaccharides and polysaccharides, they may be reduced by Tollens and Felling's solution, sometimes they may not be, depending on their chemical connectivity. That we'll study later. The first thing that we'll know about monosaccharides, the first thing that comes to our mind is the member of it is glucose. The formula is C6H12O6. The structure, as we know, right now for us even the small structure is enough, but it's better to write the complete structure because it helps. So as we can see, this is a 6 carbon monosaccharide, 1 2 3 1. Then please try numbering from the topmost carbon. This is the way of writing this structure: 1 2 3 4 5 and 6. So this is glucose. This is the way of writing the complete glucose structure, but if the structure is not required, then the short form is CHO CHOH 4 times, because there are 4 carbons in between, and then CH2OH. This is a way of writing. Okay, so at first we'll write how sugar is prepared, glucose is prepared, sorry. Glucose is mainly prepared by hydrolysing sucrose, from which we also get fructose, as we know, but we can separate it and glucose can be prepared from that. We take sucrose, hydrolyze it in the presence of H plus, which is usually HCl or H2SO4 in an alcoholic solution, and we are left with glucose and fructose. If we write the molecular formula, we know sucrose is a disaccharide, so the formula is C12H22O11. If you want to remember this, you can write it this way: CnH2nOn. Sorry, CX. It's better to write with X and Y. CxH2yOy. Now we know that it is a disaccharide, so the carbon molecules will be double the time that is there normally in monosaccharides. So in monosaccharides there are 6, so double that, that is C12, and in that case there are 6, so double it 12, but 12 cannot be found because of obvious reasons that we'll study later. So it will be 2 times of what there is in oxygen. So oxygen will be 11 and here it will be 22. So sucrose is C12H22O11, which will be hydrolyzed. So here we can see that 2 hydrogen and 1 oxygen is coming, so the overall number of carbon atoms will become C12, number of hydrogen atoms will become 24, and O will become 12. We can see that it is actually a dimer of C6H12O6. That is the formula of glucose. And fructose also has the same formula, but the nature is different. Chemically, glucose is an aldohexose and fructose is a ketohexose. We'll study about that later. And another way of preparing, first we wrote that preparation of glucose from sucrose, usually HCl or H2SO4 is used. Another way of forming is from starch. When starch is made to hydrolyzed in acidic medium at 393 Kelvin, 2 to 3 atmosphere, glucose is formed. This reaction is quite difficult to remember because already we are remembering a lot of reactions. Better to remember this reaction as it's easy. Next we come to reactions given by glucose. First, oxidation. As we know, it reduces Tollens and Fellings reagent. As it reduces Tollens and Fellings, it will itself get oxidized. Therefore, those reagents can also act as oxidizing agents. Let us write it in short form first. Kindly note the oxidation state of both the uppermost and the lowermost carbon atom because they will change. When we use Tollens reagent, I'm not going into the depths of Tollens reagents composition because we'll study that later in class 12. For now I'm just focusing on biomolecule structure. So the CHO group, that is the aldehyde group, we know on further oxidation it gets oxidized to carboxylic acid group. Fellings solution will lead to the formation of same product. This is known as gluconic acid, by the way. Gluconic acid. It comes from the name glucose, as we are oxidizing glucose to gluconic acid, where the topmost carbon becomes COOH. And copper gets reduced to Cu2O, where the oxidation state of copper is 1. Remember that. So glucose is oxidized to gluconic acid both by Tollens and Fellings solution. When we use bromine water, the same product is formed. Okay. But if we want to oxidize both this carbon and this carbon, we need a special oxidizing agent, that is nitric acid. CHO, CHOH, whole 4, CH2OH, this is glucose. When this is treated with concentrated nitric acid, this is known as saccharic acid. This was oxidation. Next we come to reduction of sugars. Mainly reduction is done by two reagents. Depending on the product we want, we change our reagent. So if we use HI along with a little heat, all the hydroxy and the aldehyde groups all will be reduced to alkane, means their alkane counterpart. So CHO will become CH3. Here we have CHOH, that will become CH2. How many times? 4 times. Last will be CH3. So what we are getting? Hexane, N-hexane, normal hexane. That is the product. If we want to completely reduce glucose, we have to use hydrogen iodide. But if we want to reduce only the CHO group to CH2OH, then we need to use sodium amalgam reducing agent. This is known as sorbitol. N-hexane, in which all the carbon atoms contains OH group each, is known as sorbitol. Okay. Next we come to oxime formation. Oxime we have already studied a little bit in class 12 aldehyde chapter. If we remember that, we can write it easily. It's better to write this way so that we can remember it. This is known as glucose oxime. Next, as this is a aldehyde group, it will show most of the reactions that aldehydes give, like another reaction, cyanohydrin formation. Cyanohydrin formation. On reaction with HCN, we know that the cyanide group goes and attacks the carbonyl carbon and it opens up. This is known as glucose cyanohydrin. Further acetylation can also take place in glucose, because we know that hydroxyl group does give acetylation reaction. These are special reactions of glucose, and so needs to be memorized, because we have not come across these type of reactions before. There are 5 hydroxyl groups in glucose, therefore we will be needing 5 acetylating agents. We are using here acetyl chloride. Can you remember another acetylating agent? Acetic anhydride 2 can acetylate here, but we'll use acetyl chloride. This is known as glucose penta acetate. glucose pentacetate. Now normally we have seen that hydrogen reacts with the only aldehyde group present there and forms the corresponding oxime. But if we use phenylhydrazine, it has been found that it forms ozazone. So there is a special reaction and we need to memorize this. This is also a part of your practical curriculum, so you need to remember this at all costs. Reaction with phenylhydrazine, also known as ozazone formation. I think in your practical copy it will be written as ozazone only, so that is why I have written here ozazone formation. We'll write the glucose molecule in a special format. We normally write CHO, CHOH whole 4, but in this case we'll write CHO, CHOH, leave a gap, and then write CHOH thrice. This makes it CHOH 4 times, but we have write it in a special way. We have to write this in a special way. So CH2OH, this is glucose. We need to use 3 moles of phenylhydrazine, remember this. Again, if you have any doubts regarding this reaction, because you are using 3 moles and it will react with only 2 moles, so the doubt may arise that why is it happening. You can come and ask me that doubt later and we can discuss. As you can see, these are just oxime reactions, but the oxime reaction is taking place in both the number 1 and the number 2 carbons. The reason behind this lies in the mechanism. It is not an exception again. There are no exceptions in chemistry actually. The mechanism speaks for everything and we don't make time for studying mechanisms, and that is the reason we keep it under exceptions. There are no exceptions in chemistry. Okay, so this is known as ozazone. We have used 3 moles of phenylhydrazine, but actually only 2 moles have entered. This is to be remembered, that one of the phenylhydrazine molecule does not add up but is used in the mechanism. Okay, this comes to the end of the reaction part. Now the structural part of glucose comes, means the configuration. When we are going to study monosaccharides, we are going to start with the simplest one, that is glyceraldehyde. When glyceraldehyde was first studied, it was found that it consists of 2 enantiomers. I think we must know something about enantiomers already, because in class 11 we have studied that enantiomers are optical isomers that are non-superimposable. Non-superimposable mirror images are known as enantiomers. So the reflection takes place here. So we can see that these two are non-superimposable on each other, and therefore as they are mirror images, known as enantiomers. These 2 enantiomers have been found to be existing in glyceraldehyde. So it has been found that one of them gives plus rotation, another gives minus rotation. What is this rotation? When a light beam is made to pass through a molecule, through glyceraldehyde solution, it's found that the light beam rotates. What do we pass through this? Partially polarized light. This is very important, that we pass partially polarized light through a optically active compound solution. For example, in this case, glyceraldehyde. The light beam rotates. Like, if the partially polarized light has vibration of electric field in this and this way, after passing through the solution, it will become this way. So we can see that the light has shifted in which direction? In left direction. So we will call it levorotatory. And if after passing it, the vibration shifts tilts slightly towards the right, then we'll call it dextrorotatory. The levorotatory is given by the sign minus, and the dextrorotatory is given by the sign plus. Now, incidentally, this is just by coincidence, it was found that the plus forms means the plus form was initially, though it was not known that which one was which. The notation was given D, and this one was notation was given L. Incidentally, it matched, but that doesn't mean that the plus sign has anything to do with D. This D is not dextrorotatory. This D is just given as a configurational notation to match with the glyceraldehyde molecule. That is, this carbon's configuration is known as D, in which the OH group will fall on the right hand side and the H group will fall on the left hand side. So if at the bottommost carbon is CH2OH, the carbon above it, that is this carbon, that is the carbon number 2, sorry, not carbon, yes, in this case number 2. So in the carbon number 2, that is the carbon next to the last carbon, has OH on the right hand side, then we'll give the notation D. But that doesn't mean that all molecules in which this OH group will be on the right side will be dextrorotatory. D that we are giving here, it is a theoretical notation. Plus that we are giving here, that is dextrorotatory, that is a practical experimental observation that has nothing to do with theoretical operations. Here in this case, the OH is on the left side, so theoretical notation is L, and incidentally it is found that glyceraldehyde gives a levorotation, that is why we have given the minus sign. This is very important, as we'll study more about optical rotations in this carbohydrate chapter. Most of the monosaccharide molecules that are aldose and are naturally found have been found to give dextrorotatory, and in all of them, incidentally, it has been found that the second last carbon contains OH group on the right hand side. For example, I'll give you, if we see the structure of glucose, focus on the second last carbon. This is the last carbon, 1, 2, 3, 4, 5, 6. Second last carbon is carbon number 5, in which the OH group is on the right hand side. What do we call carbohydrate that has, or a sugar molecule that has OH group on the right hand side? D. And incidentally, it has been found that it gives dextrorotatory, means it rotates partially polarized right towards the right hand side, so dextrorotatory. So this is known as D plus glucose. There are many monosaccharide molecules, which I'll give a chart for that. It will be better to remember it that way. Next we'll come to the cyclic structure of glucose, because glucose does not exist in nature the way that we have written here. It does not exist as a non-cyclic form, it exists in a cyclic form. Okay, So in nature it has been found that glucose exists in two anomeric forms. What are anomers? We'll discuss it later. First let us try to understand what are these anomers. Alpha glucose and beta glucose. These are the two forms of glucose that exist in nature. The alpha form has a melting point. We don't need to remember this, but I'm just trying to tell that the alpha form and beta form, though they are chemically the same, they are slightly different while showing physical properties. The beta form has melting point of 423 Kelvin, I think. This has 419, this is 423 Kelvin. When they are mixed, the melting point together becomes 303 Kelvin. Okay, so these are just numbers, you don't need to remember all this. It has been found that the alpha D glucose form, as we have said, that both of them are dextrorotatory and both of them have the second to last carbon in which the OH group is on the right hand side. So we'll write D, the alpha D glucose gives an optical rotation of, we write it this way, alpha 298 Kelvin, D. This D that I am writing, this one, this is the sodium D line, because we use sodium light and make it partially polarized and then we pass it to the solution. If we need to know more about this, we can ask me later and I can give a separate video for that. Okay, so the specific rotation has been found to be about 111 degree, that is plus 111 degree, because it is dextrorotatory, we know that. But beta D glucose, that is another anomeric form, that has specific rotation of, specific rotation is nothing, when we pass that partially polarized light, we know that it tilts the partially polarized light in a certain angle, as we have shown before here. So this tilt, here an angle is there, this angle is what we are talking about. In this case the alpha form shows now when alpha D glucose or beta D glucose is made to rest, it goes to equilibrium, that is if alpha D glucose is left free, then an equilibrium is established between the two forms. Even if beta D glucose is left free, it will, some of it will start converting to alpha D glucose, and the alpha D glucose, if left free, will start converting slightly to beta D glucose. So an equilibrium will be established between the two. When equilibrium is established in the equilibrium point, the specific rotation, as we have seen that alpha D has plus 111 and alpha D of beta D glucose is plus 19.2, we'll see a value between the two. The value has been found to be 52.5 degree dextrorotatory. So if glucose not of alpha but of the equilibrium point is 52.5 degree, so if we keep alpha D glucose separately, we'll find that a specific rotation of 111 degree is being shown. If we keep beta D glucose, we'll see plus 19.2 degree, but if we keep it for a long time, an equilibrium will be established between the two and the specific rotation of the contributory solution, that is the mixture of the two solution, will become 52.5 degree. Now we'll study that why this happens. First let us write the structure of glucose. better to write the CHO this way, so that we can show the way of attack. This oxygen atom has lone pair of electrons. It will go and attack this carbon, and this will open up. So what will be left with? I'll number it to make it more clear. So what happens is, this oxygen atom goes and attacks this carbon. This oxygen opens up and takes this proton, because we know oxygen can at a single time can only make 2 bonds. This is formed. Now if we write it in a better way, OH, H, HOH, OHH. Okay, I have numbered it. This one is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and this oxygen has gone and attached this way. The better way of writing this is this way. This is the way of writing mainly. And to write it in a better way again, these are ways in which you can rotate it. So what we'll do is, this bond we'll take it in the top, that is the bond connecting this carbon to the oxygen. We'll take it here, the hydrogen will come here and OH will come there. This way we'll rotate. Now something to note here, that why did we rotate it this way, and why did the OH molecule specifically go upwards? It could have been this too. When the oxygen atom opened up, it could have opened in any way possible. So we'll write that too. Okay, next we'll take the OH molecule. This rotation will happen. So in this case, hydrogen atom will come here. It's better to write in the same way that we have written before. First, okay, I won't do the rotations before, because that will be difficult for you to understand. I'll do it in the second step. First, let us write down. Here the H will come, here OH will come. I have not numbered, I'll number it. 1, 2, 3, 4, 5, 6. 1, 2. It is quite difficult to make this understand online, so I think you'll bear with me a little bit. Okay, so this is our molecule, and the last conversion that we have done here, that is, this will go here, this will go up, and this will go here. So each will come on the left, each will go on the right. This is carbon number 1. And at last CH2OH. Now we'll do one last rotation. First we'll do this one. So we have two molecules, this one and this one, but we'll do one last conversion because this 2 needs to be converted. This carbon, the H will go here. It's better to move this here. This will go here, this will go here, and the H will go here. We can make rotations in 3 bonds but not with 4 bonds. Okay, it's better to remember it now as a rule. Later we can understand it in depth. The oxygen atom is here. We'll do, this is one of the molecule. First of all, let me tell you one thing. This is the way of representing the cyclic structure in the Fischer form. This one and this one. These are the 2 anomers, because you will see one thing, that in both of them all the carbon atoms, C6, this is the 6th carbon, the 6th carbon, the 6th carbon, the 5th carbon, the 5th carbon, the 4th, the 3rd, the 2, all have the same configuration. That is, in the 2nd carbon, OH is on the right, OH is on the right in both cases, OH on the left, OH on the left, OH on the right, OH on the right on the 4th carbon. And the 5th carbon, the cyclic bond is taking place. Sorry, I have not written the oxygen atom, both cases. Yes, the 6th carbon is CH2OH, but in both of them only one difference is there, that is on the 1st carbon. If you see, there is the difference. In the 1st carbon, OH is on the left side, and in this case OH is on the right side. Here it is on the left side and here it is on the right side. This difference on the 1st carbon, due to the attack of the 5th carbon's oxygen atom, leads to the formation of cyclic structure which are structurally a little different. This is known as anomers. These are known as anomers. So there is an anomeric relationship between the two. Now which is which? For that we have to come to the cyclic form, that is the Haworth structure, and for that I was converting it. So this molecule has been converted to this one, and this molecule too can be converted that way, in which the hydrogen atom will go here. Sorry, made a mistake. This will go here, this will go here, and the hydrogen will come here. Everything will remain same. HOH, and the last one, this is 1 2 3 4, and the fifth carbon, the CH2OH, will come here, the H will go there, and this will get connected. This is my sixth carbon. Here 2 I'll number 1 2 3 4 5 6. Okay, so we are ready. Now what we'll do is we'll tilt it. Now this tilting needs some expertise first, learn that, and then we can continue. For now I'll continue, but you take a break here. First try to learn this structures separately till this stage, and then we'll start towards Hayward structure. So in the Hayward structure, what we need to do is take this and make it sit in this direction. So the oxygen atom is here. Next comes the first carbon, then the second, then the third, then the fourth, and the fifth carbon. Mainly the 5 carbons need to be part of the ring. The first carbon, as we have made it set down, the right side's functionalities, that is all this, will come down because the H atoms are going downwards. So H, up will be OH, down is OH in the second carbon. This is carbon number 1, this is carbon 2, down is OH, up is H. The third carbon, down is H, up is OH. The fourth carbon, down is OH, up is H, and the fifth carbon, down is H, up is CH2OH. So this is the anomer, the cyclic anomeric form of glucose. This is known as beta glucopyranose. It is written this way. We know that it is the D form, so we write D. The beta form because we have named it beta, in which the OH group is up. We'll come to the next one. We'll also write this one's cyclic form in the Hayward structure. This structure is known as Hayward structure. This is the Hayward structure of writing. We have already studied few ways of writing, like the Fisher form, the Sawhorse form. This is another form of writing, the Hayward structure. This, the name is the beta D. We know that it is dextrorotatory, so plus glucopyranose, Y pyranose. This is the structure of pyran. I think that will be enough for your answer. This is pyran, and as the structure looks like pyran, so pyranose. 6-membered ring in which one of it is oxygen atom. So 6-membered ring, one of it is oxygen atom, so beta D plus glucopyranose form. Same we'll do with this structure. We'll make it tilt, so the oxygen atom will be here and the other 5 carbons will come here, in which this one is the first carbon. So we'll write this carbon number 1. Up will be these functional groups and down will be these functional groups. Down is OH, so we'll write OH. Up is H. Left ones are up, right ones are down. In this case, OH is in the right, so down. H is down, OH is up. OH is down, H is up, and in the last, H is down, CH2OH is up. If we compare the two, you'll see there are quite similarities in it. Almost everything is similar. The second carbon is similar, the third carbon is similar. Okay, I have not numbered 2, 3, 4, 5. The third carbon is similar, the fourth carbon is 2, the same, up is H, down is OH. In the fifth carbon also is the same in both the cases, only the first carbon is different. In the first carbon, the OH is up, we call it beta D plus glucopyranose, and in the first carbon, when the OH is down, that is in this case, we call it alpha D plus. We know that it's always dextrorotatory, only the alpha and beta form changes. Glucopyranose. Okay, so these are the two pyranose forms, and these are anomers. We have studied that the alpha form and the beta form have different specific rotations, different physical properties, that is melting point. The alpha one shows 111 degree specific rotation, the beta one shows only 19.2. When they are mixed and chemical equilibrium is established. Why chemical equilibrium is established? It is quite evident that the position of OH group and the H group can obviously differ on the type of attack that this, where is that OH group? Yes, this OH group's attack mainly changes the position. If the OH group attacks and the OH comes here and H comes here, then that will become alpha form or beta form, but depending on what it is becoming. As we have seen that this has a route which is going through this way and it's becoming the beta form. So this is giving rise to the beta form, and this is giving rise to the alpha form. It's better not to remember, but to write the structures and go through the derivation, because it is not always efficient to remember all the structures. Okay, so depending on the position of H and OH group, we can see that the OH group is on the right, H is on the left. This is giving rise to the beta form, and the OH group on the left, H is right, this is giving rise to the alpha form. So the chemical equilibriums, whenever it is established, of 52.5 degree rotation is observed at last. Next we will study fructose and other structure of molecules in the next lecture. For now, it's better to end it because there has been a lot of information that has been given in this video, and it's better to digest it first.